So last time we looked at this graph, and we had talked about how entropy increases throughout a phase, and then through phase changes as we increase temperature. And so what we saw is that as we increase the temperature of a solid, the entropy increases somewhat slowly until we get to a point where we enter into the liquid phase. Okay, and we see a large, sharp jump in the entropy. Okay, so this is the point of melting. So we see our entropy of, we also call it entropy of fusion. And as we then increase the temperature of a liquid, entropy increases slowly. We're applying more heat to those molecules. They're able to move around a little faster. Eventually, they vaporize, and there's a sharp jump in entropy until we enter into the gas phase. So in general, the entropy of the gas phase is greater than the liquid phase. It's greater than the solid phase. Okay? So the very beginning of the semester, we spent a lot of time thinking about how solutions were formed. And I told you, there was a lot of things that went into it, including entropy, but I also told you just to recognize that that is a thing that you need to know is an issue, but we didn't really talk about what that meant. So now is the point where we can actually talk about what that means. If you recall these figures, okay, so if we have sort of a description of enthalpy that's required when a solution is formed, or that's used when a solution is formed. This is for an exothermic solution. The other one is for an endothermic. And you recall that we have to put heat into the solvent to sort of disaggregate it, break it apart, put space between the molecules in some way. We need to do that with the solute as well. So that's going to require some heat. And then when we mix the solute and the solvent, we actually see a decrease in the enthalpy, and that's this red line here. And for an exothermic reaction, we actually don't need to invoke the idea of entropy as to why this solution is formed. But when it comes to the endothermic, we actually do need to think about the entropy that increases as we form the solution. Now, for both an exothermic and an endothermic solution-making process, the entropy is going to increase as we form the solution. Okay, that is always going to be the case. And so the reason being for that is we now have a solute and a solvent that are mixed together. One way to think about this is that specifically with the solute, it was originally in this nice crystal structure, okay? Maybe it was a solid, so it didn't have much entropy anyways. There were only a few microstates where those molecules could be. And then we put it in solution, and we essentially increase the available volume for those microstates of that solute. So simply the available microstates increases for the solute, the entropy increases, and so that is one reason why the solution formation process is favorable. Yeah, okay. Does that make sense? All right, so essentially we're increasing the number of microstates, and it's actually much more disordered. So we have a solvent, even if it's in the liquid phase, there's only solvent in there. We have a solute, if it's in the solid phase, it's highly organized. We mix those together, combine some molecules, you can think about that as more disordered, okay? Okay. No, same sort of idea here being shown. Again, okay, so there are a number of factors that affect the possible number of microstates for a given system. And those are temperature, volume, number of moving particles, and the number of reactants and products for a given reaction. So for temperature, as we've seen, we're looking at the phase change diagram. As we increase the temperature, the entropy, which we're going to give the symbol S, the entropy increases. The number of microstates increases. Whenever we say entropy increases, that means the number of microstates has increased. As we increase the available volume, that also increases the entropy. So increase V for volume, we increase S for entropy. Right? Especially if you think about this as a gas. If you have a gas in a tiny area versus gas in a larger area, there's many more places for those gas molecules to exist in the larger area compared to the smaller area. Okay? The number of particles. And we said specifically independently moving particles. So if we increase the number of particles, the entropy increases. Again, more possible things to be in more possible places, to have more possible energies, that kind of thing. And then for a reaction, typically what we will see, especially when we have the gas phase, is that the side of the reaction arrow, the side that has the larger number of species, larger stoichiometric equivalents, is going to have the greatest amount of entropy. So we did something similar to this when we were thinking about what? Le Chatelier's principle and volume changes, I believe. So this is along those same ideas. So the entropy is going to increase as the number of gas molecules increases. Entropy increases as the number of gas molecules increases. So in our two examples here, 1 and 2, in example 1, we have 2NO plus O forming 2NO2, and that's the gas phase as well. So we go from having 3 molecules reacting, and we're forming 2 molecules. So because we have 3 moles of gas on the reactant side, there's actually a greater amount of entropy on the reactant side. Okay. In the second example, we go from 2 molecules of H2O2, hydrogen peroxide, to a total of 3 different molecules, 2 water and 1 oxygen. So this product side has greater entropy. Okay? So if there's more molecules, so this goes back to number 3, number of independently moving particles. So if there's more particles or more molecules, we have greater entropy. Okay? That will be something you'll be asked. Let's kind of do an example here, and I want to define something. When we say that delta S is positive, that means it has greater entropy. So sometimes if we have it like a negative number, it means something. This time it's actually correlated, so increased entropy, greater positive number. Okay. So for these 4 examples, which one would have essentially a delta S of reaction is positive, meaning there's more entropy on the product side. Whoop. Compared to the reactant side. think that's right. Yeah. And for these cases, we really only need to consider, well, not in every single case, but keep in mind that if you have a reaction that has mixed phases and the phase includes gas, the entropy of that gas phase is going to be much greater than a solid or a liquid. Okay? So take a look at A, B, C, or D. Which one do you think has the product side has the greatest entropy? All right, so in example A, we have aqueous silver ion, aqueous chloride ion forming solid silver chloride. And so for this reaction, we go from a sort of reactants which are in the aqueous phase, they have a lot of microstates, places where they can be in solution, to a solid. And so here we actually see a delta S for a reaction would be negative. Okay. For the next example, we go from the solid phase to the gas phase. And as we saw with that diagram showing the entropy with temperature as we go across phases, this is going to result in an increase in entropy. And so for B, we should see a delta S that's positive. I'm going to do plus VE for positive. So this is actually the example, but we're going to look at the other two, or this is the answers. We're going to look at the other two examples and see why they are not the case. In C, we go from 4 total molecules of gas down to 2 molecules of gas. So that's a decrease in entropy for that reaction. And then in D, we go from the liquid phase to the solid phase with water. And again, that's a decrease in entropy. Okay. Questions on that? Okay. All right, so this is a picture of Ludwig Boltzmann's tomb in Vienna, Austria. He has this very famous equation written on his gravestone. And this equation relates entropy to microstates using the Boltzmann constant. So he's responsible for this equation. And essentially what this says is, again, if we are sort of equating microstates, which is given by the symbol W here, to entropy, that as the entropy increases as the number of microstates increases. So it's actually a logarithmic increase. If we were to plot this equation, we would see microstates, put microstates on the x-axis, entropy on y, and we would see an exponential curve. Okay, so that's given by the natural log. Right. The relationship between entropy and microstates is given by the Boltzmann constant, 1.38 times 10 to the minus 23rd joules per Kelvin. Okay, so that's just somewhat interesting to have an equation on your grade. Okay, so If you notice on the plot that I keep referring to, where we had entropy and temperature, at the origin of the graph, we were at 0 entropy at 0 degrees Kelvin. And that is the third law of thermodynamics. This says that a substance is perfectly crystalline at 0 degrees Kelvin, and it has an entropy of 0. It's in perfect order. It essentially means it has no thermal motion and only one microstate is possible. Okay. If we assume that this third law is a law, which we should, we can derive the standard molar entropies. And from that, we can determine the entropies for various reactions. So the standard enthalpy is a value relative to 0 Kelvin at 0 energy. So it's sort of like our baseline. We're an offset from that for these particular molecules or species that we're going to look at. To actually derive those, we are going to use them, though, to determine entropies for reactions. But we'll get there in a second. So we usually see standard molar entropies at 25 degrees Celsius, not at 0. Okay, so not at 0 Celsius or 0 Kelvin. 25C is what we usually will use. And in terms of trends, we sort of talked about this already. What we're going to see is that the standard molar entropy for gas is greater than that for liquid, is greater than that for solid. We should also see that the standard molar entropy increases with increasing molar mass. Again, this goes back to the number of possible microstates. Even if we have atoms that are bound together, creating a larger molar mass, those atoms will still have greater number of electrons, which are moving, and those can have microstates. Okay, so what we see is increased entropy with increased molar mass. And then following along with that, if we have more atoms in the substance, we're going to have a greater entropy. So the way that we calculate entropy for a reaction is the same way we calculate the change in enthalpy for a reaction. So we're going to use those standard molar entropies, which is given by S naught, for the products and the reactants, multiply by the stoichiometric coefficient, moles, and we'll do sum of the products minus sum of the reactants. So we saw this same formula essentially for enthalpy, except we were using enthalpies. And if we see a positive delta S, we see an increase in entropy for the reaction, just like the example we did, and a negative, we see a decrease in entropy. So sometimes, but not always, you should be able to predict the sign of the delta S. Sometimes it's a little bit more complicated. For instance, if you're working completely in the aqueous phase, it can be really difficult to predict. That's not something we would necessarily ask you to do without having actual values. But you can predict for these three cases if a molecule is broken down into smaller molecules, so a decomposition reaction. A reaction has more moles of gas on the product side than the reactant side. We'll see a positive change in entropy, or when going from liquid to a gas or solid to a gas, or solid to a liquid. All right, you want to do some more predicting? I'll give you 1 minute to do some predicting. Garrett.
So it's not a question for like these, but like how important is like the phase change versus like the increase in number?
How important is the phase change versus the increase in number of moles? Is that what you said?
Like you have this is like one gas thing, and it turns into like two liquid things.
Yeah, okay. We wouldn't ask you that kind of question because there's no obvious answer. All right, so for these, what do we get? So 2SO3 going to 2SO2 and 1O2. Increase in entropy or no? Yes? Yes. All right, what about the next one? Here we have ethanol plus oxygen forming carbon dioxide and water. Decrease. Yeah, so here the most important things are the species in the gas phase. And so we go from 3 moles of gas to 2 moles of gas. So we're going to see a decrease in entropy. Anyone want to counter on that one? That's probably the most confusing one on here because we also have the one liquid molecule on the reactant side, and we have a total of, and we have 3 on the product side, total of 5 on the product side. But for these, the number of gas molecules are really what matters because the entropy of those is so much greater than that for liquid. Okay, so that's why this answer is the way it is. And then for the last one, going from a gas to a solid, decrease. Cool. Okay. So here we can calculate delta S4 reaction now with actual values. Again, these are values that would come from a table. So if you have standard molar entropies for the species that are in the reactants and products, you can calculate delta S for a reaction.
If you have liquids or solids in a reaction, you don't count them?
Yeah, in that previous example, if you have liquids and solids in the reaction and you're just trying to predict without doing the math what the change in entropy is going to be, you can ignore those. Oh, for this? Oh, no, you do need to leave them in. Yeah. When we're actually calculating with numbers, we are going to incorporate those species with liquids that include liquids and solids. So everything will go in. Good question. Okay, so, all right. So we're going to take the number of moles times the entropy for the products, sum those up, and then subtract those of the reactants. So in our equation, we have our products are 2SO2 and O2. So I'm going to take the 2 moles of SO2, multiply it by its standard entropy, which is given by 248.1. This is joules per mole Kelvin. Okay, I'm going to add up the 1 mole for oxygen times the 205.0 standard molar entropy. And from all of that, we're going to subtract the 2 moles of SO3 times the 256.7. Okay. In this equation, we should see an increase in entropy, so we should see a positive value. And going through all of this math, we end up with 187.8. What are the units? Joules per, it's just joules per Kelvin. And it's just joules per Kelvin because we've multiplied by moles inside the bracket. Cool. And again, positive value, that's what we predicted, so that's good. Questions on that? So we've been talking about entropy. We talked a little bit about whether a reaction is, what it means for a reaction to be spontaneous. And now we can use something called Gibbs free energy to help us determine if a reaction is going to be spontaneous. And Gibbs free energy, or G, delta G usually, the change in Gibbs free energy, is equal to delta H, where H is the enthalpy, change in enthalpy, minus T, which is the temperature in Kelvin, times the entropy. And just so we know what all of those letters are, okay? So if we know the enthalpy and the entropy for a given reaction, we can predict its free energy. And from that, we can predict if a reaction is going to be spontaneous. So the way we're going to be able to do that is if the value of delta G is negative, the reaction is spontaneous as written. And as you recall, I talked about when we have a reaction written in a certain direction, it can be spontaneous, for instance, in the forward direction, but that means the reverse direction is non-spontaneous. So if we take iron and it forms iron oxide, it rusts. That's a spontaneous reaction in the forward direction, but it is not spontaneous or non-spontaneous in the reverse. So iron oxide doesn't spontaneously reform iron, okay? So delta G is negative means the reaction is spontaneous as written, okay, with reactants going to products. If delta G is positive, the reaction is non-spontaneous as written. And what do you think it means if delta G is equal to 0? Yeah. Oh, sorry, there's two of you. Go ahead. Say it together. Go ahead.
I don't know, that's not what I was going to say, so I was going to say.
Oh, I didn't hear anything. What? I missed it. Who said what?
I said no reaction.
No reaction occurs? That's what you were going to say?
No.
What were you going to say?
I was just going to say that it's like, it's an equilibrium, like those sides are.
Yeah. So that's what happens. So if delta G is 0, it's not going to proceed in either direction, okay? So that means we're at equilibrium. Sorry for making that much harder than it needed to be. Okay. We're going to use that to our advantage later on too, and be able to determine the temperature at which a reaction goes from being non-spontaneous to spontaneous. We can actually force that to happen with heat. Okay. All right, so there's two ways to calculate Gibbs free energy. The first way is if we know delta H and delta S, we can then use this equation to calculate delta G. And sometimes you'll be asked to calculate delta H through tabulated values of the delta H of formation. So this was essentially this equation, but with delta H's in it. The other way is there are tabulated values for Gibbs free energy for various compounds. So you could look up the Gibbs free energy for those and calculate. Excuse me. So when we are looking at the delta G's of formation for various substances, this is very similar to what we see with enthalpy, is that the stablest states, which is often the elemental form, but it could be a diatomic form. We're going to see that for those, delta G of formation is equal to 0. So if we have elemental sodium, it's delta H of formation is going to be 0. If we have chlorine gas in its stablest state, that's Cl2, that delta G of formation is going to be 0. Okay. Not that you need to memorize that, but it is just something to recognize. Okay. So essentially, Gibbs free energy, or delta G, can tell us how useful a reaction might be for doing work. Only those reactions that are spontaneous can be useful for doing work, because non-spontaneous reactions we would have to put energy in some way. And a good example of this, and something we're going to get to next chapter, are batteries. So you put a battery, you put your battery in your phone, you charge your battery, right? You charge your phone. As you're using the phone, the phone uses the energy from the battery. That's a spontaneous reaction that is making that battery work. And as you know, your phone will spontaneously recharge on its own, so you have to put energy in by plugging it into its charger. That's forcing that non-spontaneous reaction to occur. Okay. Okay, so the most possible useful work at constant temperature or pressure is given by the term W max, work max, and it is equal to delta G. So we could know the number of joules per Kelvin of energy that can come from a reaction, and that is the amount of work in joules that can be done. One thing to note is that we can never actually achieve maximum work, and that's because we could have like these sort of side reactions. Heat can form, that can be sort of a hindrance, and so that's sort of maximum work is only a hypothetical. Okay, so let's think about the change in free energy during a reaction. And we'll go back to our reaction progress diagram, where we have reactants on the left and products on the right. And we have some a y-axis that has a magnitude of G, okay? Delta G is going to be the difference between where we start on the reactant side and where we end on the product side. So this is essentially delta G. Now what you see for this type of reaction, this is actually a spontaneous reaction. And how do I know that? If you look at where the lowest value of G lies, it's closer to the product side, okay? Which implies that we are able to produce a lot of products until we get to the lowest value of G, okay? And we said that when we're at delta G equals 0, we're at equilibrium, okay? The reaction doesn't proceed in either direction. And that is where that lies in terms of the reaction progress tells us about the spontaneity. Okay, so the other thing to note is as a reaction proceeds, a spontaneous reaction, the free energy decreases, so we have less and less energy until we get to the bottom of this hill into the valley here. If we wanted to force this reaction to form more products, we would have to put more energy into the system. Okay? And if we're thinking about an equilibrium, going back to that concept, and relating equilibrium and Gibbs free energy, for this type of spontaneous reaction, or this type of reaction, if you'll recall, whoops, I wrote that backwards. Q is less than K when we have more products than reactants. Q is equal to K at equilibrium, and Q is greater than K when we have too many products. So we're going to start thinking about incorporating equilibrium into our thoughts on these reaction progress diagrams with Gibbs free energy. All right, so here's a way of thinking about this in terms of potential energy. If we have a sphere at the top of a hill, or a rock at the top of a hill, we could push that down, and it's going to find its equilibrium position at the very bottom of that valley. It wouldn't end up on the side of the other hill, right? Same sort of thing here with a chemical reaction. We end up in the valley, all right, in terms of free energy and progress of the reaction. When we look at our ammonia reaction, so the formation of ammonia, N2 plus 3H2 in equilibrium with NH3. At some point we get to an equilibrium mixture. If we start with purely reactants, okay, we're going to go down that hill to get to equilibrium. If we started with only product, we could actually go down the hill and form some of those reactants. Okay? Those are both spontaneous in those written like this, if, well, certain conditions apply. But we don't need to think about that too much. Let's compare then what we know for a spontaneous reaction for that of a non-spontaneous reaction. For a non-spontaneous reaction, we're going to have a delta G that is positive, which means the Gibbs free energy of the products is going to be higher than that of the reactants. So I'm going to put 2 points on here, a lower point on the reactant side and a higher point on the product side. For a non-spontaneous reaction, that means it doesn't really proceed towards the products. Okay, we do not form a lot of products. We might form some, but not a lot. Okay, so the way we sort of represent that is we're going to have a valley close to the reactants side. And if we draw that in, that's okay. That's an okay drawing. It might look something like this, where our lowest point is where we have equilibrium. Okay. And again, the delta G in this case is a positive number. Here, when we when we get to equilibrium, and if we would want to try to form more products, we would have to put a lot more energy into the system in order to do so. So again, non-spontaneous reaction, the reactants are favored. Questions on either of these diagrams? Yes?
Is it possible to have like a symmetrical one? It's just around one.
Yeah, it would be possible to have a symmetrical free energy curve, and that would essentially mean that at equilibrium you have equal amounts of reactants and products. Yeah. Now I don't know if that means that we would call that reaction spontaneous or not spontaneous though, so ambiguous. Okay. And any other questions on those? All right, so let's actually relate free energy and equilibrium with an equation now. We can relate Gibbs free energy to the equilibrium constant, and that equilibrium constant can be any of the K's. Okay, it could be RKA, KB, KSP. We talked about KF. We used at the very beginning of our equilibrium chapter Kc for concentration, Kp for pressure, but essentially these are all K. All right, so equilibrium constant. The way we, let's see. Let's start with this equation. Yeah, we'll do that. So if we don't know that a reaction is at equilibrium, that's when we use Q, right? So you remember calculating Q and comparing it to K to figure out if our reaction is at equilibrium. So we can relate Gibbs free energy and Q using this equation here. But we know that delta G is equal to 0 at equilibrium. And this is the delta G without the not sign. Okay, this is this delta G. So if we want to calculate delta G naught at equilibrium, we know that delta G is going to be 0. And so we can set that equal to 0. And if we say we're at equilibrium, then we can use the equilibrium constant K. And we can rearrange this to say delta G naught equals R times T times the natural log of K. All right. So essentially what this tells us is that we can use an equilibrium constant to predict the free energy for that reaction. And just to point out, this R is the 8.314. Oh, I forgot a negative sign, didn't I? Yes. That should be negative. 8.314 joules per mole Kelvin, and the T is temperature in Kelvin. Okay, don't forget the negative sign, I almost forgot there. So let's actually calculate the equilibrium constant for rusting of iron. So we're given delta G's of formation. So from these, you can calculate delta G naught for the reaction. And we'll take the products times their stoichiometric coefficient minus the reactants summed up. And because the delta G for iron, which is its elemental form, and oxygen, which is in its stablest form, those delta G values are 0. So the delta G for the reaction is going to be given by 2 times minus 743.5. And we'll get minus 1,487 kilojoules per mole. Or excuse me, kilojoules. Okay. So using this for our delta G of reaction equal to minus RT natural log of K. So use that, to give you a minute there to calculate the equilibrium constant K. All right, what do we get? $1.82. 1.82 for K. Anyone get something different? What'd you get? Yeah. Yeah. Does your calculator fail to do this? Perhaps you got overload? Okay, so sorry, Garrett. When you calculate this, our delta G of reaction convert to joules. I'm wondering if maybe we forgot to convert to joules. We're going to have minus 1.487 times 10 to the 6 joules equals minus 8.314 joules per mole Kelvin times 298K times natural log of K. So if we divide both sides by all this, we're going to get 600.2 equals natural log of K, I believe. And then if we want to get rid of the natural log, we'll use E. And to do E to the 600, your calculator will most likely overload, and you can't actually calculate it. So what that means for this Rustin reaction is that the equilibrium constant is so large that we can't calculate it, essentially. And we know how spontaneous and how likely iron is to rust. So that's sort of what that is pointing out in this case. Another thing I want to mention, especially from that previous slide, we have delta G and delta G naught. Okay, so what does this naught sign mean, the small zero? So this means we're at standard conditions. Okay, standard conditions are 25 degrees Celsius, 1 atmosphere of pressure. And so we're typically going to be at those conditions for the work we're going to be doing. Okay. The delta G without the naught sign could be under any conditions. Okay, so that's sort of the difference there. All right. All right, we're going to stop here today.